Okay, in this video, we're going to talk about big sigma, which is the symbol we use for sums. This is a printed big sigma. That's the way it looks. As I was printing it, I thought it kind of looks like an M on the side, but it is not. It's a sigma. It is a Greek letter. So it is, there it is. This is the sigma we're going to use. So anything that looks like a sigma is intended to be a sigma. Um, in order to work with sigmas, we have to first understand sequences, which is what we covered in a previous video, a sequence. And so what we do with a sigma is add elements of a sequence. So this sigma notation is used to add several elements of a sequence. Okay, so here goes. The sigma notation, and by that I mean the big sigma notation, is used to add elements of a sequence. And so we use an index that runs over the number element of the sequence. So pretend you have a sequence, that starts with A1, A2, A3, A4, and so forth, forever and ever and ever. Okay, so what we define this symbol, so that's why I wanted to show you a printed one, because sometimes when I draw it, it doesn't look as pretty as a printed one. Here's how it looks when it's pretty. This is just my version. And sometimes I would put little ends to it, like this one does, the printed one. But oftentimes I won't. So that's why I mentioned earlier, anything that looks like a sigma is a sigma. Okay, so this means we're going to have AI. So this is an example. Let's label this as an example 1. But we cannot, at least not yet, add every element in the sequence. We want to start at one point and end at one point. So we use the index I, and in the bottom of the sigma, we put down where we start. Say we start at 5, okay? And then at the top of the sigma, we put where we end. But we don't say I equals 5. We can say just the number without the I. So let's say 9, just to give an example. So this is read as the sum of the AIs from I equals 5 to I equals 9. So this is read as the sum, very important sum, of AIs from I equals 5 to I equals 9. All right. I is called the index. It's called the index. Okay. So in this case, what we mean specifically is A5 plus A6 plus A7 plus A8 plus A9. Be careful, because it looks like we are adding only 4 elements. We're not. We're adding 5 elements, because the 5th one counts. So we start with 5, 6, 7, 8, 9. That's 5 elements. 5, 6, 7, 8, 9. If you subtract though 9 minus 5, you end up with 4. 9, 8, 7, 6. But then we're counting the A5 that we're starting with. So watch out. And we always go up whenever we have a summation. like this one, we always go up by whole numbers for the index. So we don't go from 5 to 5.5 and then say, no, 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 no. Because we have a sequence, and the sequence has whole numbers as inputs. The outputs may be anything, but the inputs have to be natural numbers. They could actually be integers, but let's keep things simple. Now, the first thing, well, I don't know if it's the first thing, but one thing I want to clarify is that it doesn't matter what index we use. So I is called the index, but as long as we stay consistent, then it does not matter what the index is. Index is. And let me show you. So we have this sum. Okay, so it's still the same example. Yeah, still in example 1. The sum of the AIs from I equals 5 to 9 can be also written as AK. Oftentimes people use K, from K equals 5 to 9. Same thing. Don't get confused. If you see that with an I or that with a K, as long as we're consistent, A sub I from I equals 5 to 9, that means A sub 5, A sub 6, A sub 7, A sub 8, A sub 9, and then we stop at 9. Or from K equals 5, same thing. A sub 5, A sub 6, A sub 7, A sub 8, A sub 9, and then we stop at 9. And then you can use any other letter as long as we're consistent. So, a lot of people use J sometimes but again, we got to start with J equals 5, and then those are exactly the same thing. Do not get confused with the index. And some people even put N from N equals 5, A sub N to 9, same thing. You can, those are the common letters. I, J, K, N, M are I would say, the most common letters, but you could use anything really, A sub M. So all of that is the same. All are the same. Okay, so all are same thing. Okay. Now, if you put down the sum of AI from K equals 5 to 9, that is confusing. That doesn't seem to make sense. This is confusing. Yeah, because it could conceivably happen that the I has nothing to do with the K. So watch out. We typically don't put this down. I guess in some cases we could, but yeah. This brings me to a second example. Well, before we do some weird example, let's do some normal examples. Now, most of the time we have a formula for this. So second example, how about the sum of 2n from n equals 5 to 9? Now, those correspond to the even numbers. Okay, so there are two things going on here. There is behind the scenes, there is a sequence. Behind the scenes, there is a sequence. What is a sequence? When n equals 1, we have 2. When n equals 2, 4. 6, 8, 10, 12, 14, 16, 18, 20, and so forth, 22, etc. Okay, so that is the sequence. It goes forever. Now, how do I know that is the sequence? Because that we think of 2n as a sub n. It is just the formula for the elements of the sequence. So when n equals 1, you have 2, 4. When n equals 2, you have 4. When n equals 3, you have 6, and so forth. Well, what we are doing is adding the elements starting with the fifth element. This is what this says. 1, 2, 3, 4, 5. Start here, fifth, sixth, seventh, eighth, ninth element. So we want to add those 5 elements together. So this is a shorthand for 10 plus 12 plus 14 plus 16 plus 18. And then we have to add those terms together. So 10 and 18 is 28, 12 and 16 is 28 again, and 14, I think that is 28 and 28 is 56. Yeah, that is going to give us a grand total of 70. So this sum is 70. Okay, and we can use different formulas there. Example 3. Okay, the sum from now, oh, I did use n last time, so I'm going to use a different letter from 5 to 9 of 2n plus 1. So that means we're going to add the elements of this sequence, the sequence whose formula is 2n plus 1. Okay, so behind the scenes, there is a sequence, an, and that is the formula, 2n plus 1, which means when n equals 1, we have 3. So 3 is the first element in the sequence. And then when n equals 2, 5. When n equals 3, 7. Well, when n equals 4, 9. When n equals 5, 11, and so forth. 13, 15, 17, 19, 21, well, and so forth. Now, what this summation sigma notation means is that we're going to add only the elements starting with the fifth element and ending with the ninth element. 1, 2, 3, 4, 5. So we start here, 2, 3, 4, 5. So this is the same thing as 11 plus 15 plus, oh, I skipped one. Yeah, there should be a 13. Those two should be reversed. Sorry about that. I skipped. It should be 11, 13, 15, 17, 19. So the fifth, sixth, seventh, eighth, ninth. I'm thinking how much it is. If I'm not mistaken, that is 75. Okay. Example 4. Let's say we want to add j from j equals 500 to 504. The elements to n. Okay, so now I'm changing. This is similar to example number 2. Okay, and we're adding 2n, except that we're starting at a different value, 500. Now there's a sequence, and here's the sequence. The sequence is 2, 4, 6, 8, 10, and so forth. The even numbers starting with 2. But we're going to start with 1,000. Oh, there's a mistake here. See? I'm going to cross that off. That is a mistake. Um, I'm not being consistent. If I have J for the index, then J should be also part of the formula. J equals 500 to 504. Sorry about that. But it is a good example. So I'm just going to box that and so that it's out of the way. Pretend that it's not even there. Okay. So this is really what we have. 2J. So those are the even numbers starting with 500. With the 500th element of that sequence of even numbers that start with 2. But of course, we're not going to start with 2 and then count 500 of them. That's going to take too long to figure out what the 500th element is. What we do instead is we just figure out the actual number. So 2 times 500, pretend that is the J is 500. That's what this means. Assume J is 500, and that's going to give us, so that is equal to 1,000 plus. And then when J equals 501, multiplied with 2, we got 1,002. And then with 3, 1,006. 4, 1,008. Wait. Oh, I'm missing 1, the 4. Boy, this is interesting. I skipped the 4. There we go. So we go 1,000, 1,002, 1,004, 1,006, and then 1,008. Yeah. So that is the sum from 1,000 to 1,008, and we need to add those numbers. Well, we know the answer is going to be 1, 2, 3, 4, 5,000 and change. In fact, it's not going to get up to 5,100. So that is nothing above 1,000. 2 and 4 is 6, and 6 is 12, and 8 is 20. So we know we're going to end up with 5,020. That is our final answer for that sum. So even though we start with 500, we're not going to start the sequence with the first element and second element and so forth. We just do we just start whatever we need to start. Now there is one example that is confusing, and I want to make sure we know it. It is very likely I'm going to ask you this in quizzes or tests or assessments. So make sure you know this following example. Okay, say we have the sum from k equals 5 to 9 of 13. Okay, now 13 doesn't have any k. You may be thinking, hey, that's confusing. It is, but it's a valid thing. So is this confusing because there's no k? In this formulas, there's a k, and the index shows up in the terms of the summation. But here, the k doesn't show up. The index doesn't show up. Now, this means we are dealing with a constant sequence 13. So this corresponds to a constant sequence. By that, what we mean is the first element is 13. The second element is 13. The third element is 13. The fourth element is 13. The fifth element is 13. The sixth element is 13. The seventh element is 13. The eighth element is 13. So all the elements, it doesn't matter, the 1,000,000th element is 13. It doesn't matter how far you go or how close you are to the beginning. All the elements are going to be 13. So this really means adding 13 from the index 5, so this corresponds to 5, plus index 6, plus index 7 plus index 8 plus index 9, and that's where we stop. 5, 6, 7, 8, 9. There we have it. So we are adding 13 this number of times from 5 to 9, which is going to be 65. Okay. So the sum of 13 from 5 to 9 is 5 times 13, which is 65. Yeah. Make sure you know how to do those examples. Okay. So for instance, let's say we are example 6. Let's say we're adding the number 7 from n equals 2 to 20. Okay, that's a tricky question. Now, that means we're going to add 7 plus 7 plus 7 plus a bunch of 7s. So you know we can just figure out how many 7s we have, and then we multiply by 7, and then we're done. But it is a little tricky, counting sometimes is not easy. People think, oh, counting is easy. No, 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 depends. Sometimes counting can be difficult. It's not simple. So this is 2. Okay, so I guess we can use our fingers and say, well, start with 2 and then end with 20 and just figure out how many there are. So we can say 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So it looks like we had 19 of them. Because we start with 2 and we end with 20. Now, somebody could say, wait a minute, 20 minus 2 is 18, but you got 19. Yes, but we're counting the 2 itself. And consequently, we have to add 1. If you actually write down, and let's do it just very, very quickly. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And if you actually count, starting with 2, how many we have? Well, let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And sure enough, we have 19 elements. So this sum is 7 plus 7 plus 7 plus 7, 19 times, which of course, the answer is 7 times 19. And I'm going to use one of these little calculators to multiply 7 times 19. 7 times 19 is 133. So that is our final answer, 133. I guess another way to do that is to say, well, we can just do 7 plus 7. So that's 2 plus 3, 4, 5. Oh, wait a minute. Why don't we just do it the other way? Start with, this is the second, starting with 2. So 2. And then 3, 4, 5, 6, 7. I don't know. That's one way to do it, but I think that is more complicated. So be careful. This is an interesting example. 7 rather, example 7. How about the sum of 7 from k equals 13 to 30? That's an interesting problem. Okay. Or even better, 130 to 300. There we go. So we know this is going to be a bunch of 7s added together. 7 plus 7 plus 7 plus, well, a bunch of them. I'm not going to write them, all of them down if they're more than 100. Okay. So how do we know how many 7s are those? So based on the previous examples, we know that if we have an index, we can subtract 300, take away 130, that's going to be 170. So it looks like it's 170, but no, it's not 170. I'm not going to put a zero because we have to include this element, um, the 130th element. So we really have to add one. Just like up here, 20 minus 2 is 18, but then we add one more because that is the second element. So we have 171 times 7, and we can do that here on the paper. 171 times 7. Well, 7 times 7 is 7. 7 times, no, 7 times 1 is 7, rather. 7 times 7 is 49. We carry 4. 7 times 1 is 7 plus the 4 that we carry is 11. So we have 1,197. So this sum equals, I'm just going to put the answer here, 1,197. Okay. Some sums are difficult to figure. If we have a sequence that is not easy to plug in numbers into, such as the Fibonacci sequence. Okay, so example 8, pretend you got the Fibonacci sequence. So 1, 1. Remember how we do that. The next element after the first two is the sum of the previous two. So this element is the sum of the last two. The next element is the sum of the last two. 1 plus 2, 3. The next element is the sum of the last two. 5. The next element is the sum of those two. 8. And so forth. 13. And then those two together is 21, etc. So this is a difficult sum if we need to add numbers that are far out. So for instance, from 5 to 9, let's do that. So, let's pretend that is the sequence AN. Okay, so that's a symbol for sequence. And so we want the sum, from N equals 5 to 9. Okay, so we want to start with a fifth element. 1, 2, 3, 4, 5. The fifth element happens to be 5. That's a pure coincidence. Plus 8, plus 13. So 5, 6, 7, plus 21. The next one is not on my list, so I have to figure out what it is. Okay, so let's see. The next element is the sum of those two, so that is going to be 34. Okay, so we just need to add those 5 numbers and then we're all set. This is the 5th, 6th, 7th, 8th, 9th, starting with 5th and then with the 9th element. So let's see, that's going to be 13 and 13, 26, 47, 47 and 34. I'm going to do that over here on the side. 47. Wait, did I do that correctly? 13, 26, 47, yep, and 34, 11, we carry 1, and so that's going to give us 81. So the answer to this sum is 81. Final answer. Okay. There are sequences that are tricky and for which perhaps we have to use a lot of common sense. So suppose you are given the sequence A sub n. I'm going to introduce a notation. I hope you are okay with this. So when we put down A sub n like so, we include from n equals 1 to infinity. This is a new notation I'm introducing. And this means that we have a sequence of elements A sub n where n starts with 1 and doesn't end. So infinity in this context and many, many contexts, it means that the sequence doesn't end. So without end to it. All right. So I'm going to introduce a sequence from n equals 1 to infinity, and it will be 0, 1, 2, 0, 1, 2, 0, 1, 2, 0, 1, 2. Well, you get the idea. The pattern is, well, once you get to 2, you start all over with 0, 1, 2, and then 0, 1, 2, and 0, 1, 2, forever and ever and ever. So that is an infinite sequence. And the goal right now is to figure out how much the sum is from n equals 1 to 100 of the a sub n. Okay, so that's okay, what I would suggest students do, you don't have to do it, is to pause the video, try to figure this out on your own. Add the first 100 elements. Mind, this is the first element, second, third, fourth element, fifth, sixth element, seventh, well, and so forth, all the way up to 100. The sequence keeps going on and on and on forever, but just add the first 100 elements and see how much that is. I think that is a good challenge. So pause for a moment, and then continue watching the video to see if you end up with the correct answer. Okay, so I'm assuming you already paused, you came up with an answer. All right, if not, pause it and try to figure that out on your own. Make it a challenge. It's a new problem. You got to sequence 0, 1, 2, 0, 1, 2, on and on and on like that. Add the first 100 elements and try to figure it out on your own. Anyway, so now we're back. So this is one way to go about it. Every third element is 2. 1, 2, 3, 4, 5, 6, 7, 8, 9. So let's notice a few things about this. Every third element is 2. Okay, how many third elements are there from 1 to 100? Well, there is 3, 6. Those are the multiples of 3. That's what I mean by third element, and 9. And all the way up to, well, the last one up to 100 will be 99. So how many of those are there? There's a few different ways to go about it. But one way to go about this, to counting those, other than actually doing 3, 6, 9, 12, 15, 18, 21, and so forth, we can rewrite them differently. This is 1 times 3. This 3 is 1 times 3. 6 is 2 times 3. 9 is 3 times 3. Well, all of them are something times 3, but the thing is that the first factor is already counting for us. The next number would have been 12, which is 4 times 3. The next number is 15, which is 5 times 3, and so forth. So the 99 is 33 times 3. So we know there are 1, 2, 3, all the way up to 33 third elements, which means there is 33 twos. So this is equal to, I'm starting with the twos, 2 plus 2 plus 2. They're not in order, mind, not. So the sum is not in order. In order, I'm rearranging them, just counting the twos, plus a bunch of twos. How many of them? 33. Okay, and that takes us all the way to the 99th place. Well, to the left of the threes, rather to the left of the twos, there's always a 1. There's a 1 always to the left of the twos. So for every 2, actually, I'm going to continue this I'm running out of space, so I'm just going to cross that for now, and I'm going to start all over here. The sum of a sub n's from n equals 1 to 100 is equal to, first, let me write them in order. 0 plus 1 plus 2 plus 0 plus 1 plus 2 plus all the way up to, 100 of them, 100 individual elements. Okay, and that means there is going to be, well, that's another way to put it. There's going to be 33 of those sets. 0, 1, 2 is one set. 0, 1, 2, second set. 0, 1, 2, third set. 0, 1, 2, fourth set. Well, there's going to be 33 of those. I guess that's another way to put it. This is equal to 33 of 0 plus 1 plus 2. Now that gets all the way up to 99, but what is after 2? 0 again, plus 0. Okay, so now I guess this is another way to put it. I was going to continue this. I changed my line of thought. Sorry about that. One way to go about it, I realized this is probably easier. One way to go about it is to say, well, there's 33 twos, and then prior to the twos, to each two, there's a 1. So there's going to be 33 ones. But that is the same thing as this, 33 twos and 33 ones and 33 zeros plus an extra 0. So that is really 33 times 3. Oh, what a coincidence. That is 99. Yeah, 33 times 3, which is 99. So the sum of the first 100 elements of this sequence is exactly 99. No more, no less, exactly 99. Some people are going to say, well, what is the formula? See, that's one problem I have with math, or with people who overuse math. That is what I call overuse of math, where they just have to go for the formula and everything has to work just by the formula. No, 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 no. There is something that is above formulas, in my opinion, and that is common sense. The formula can tell you many things, and it is useful, practical many times, but then you gotta put common sense where it belongs. Yeah, yeah. Anyway, that's just my my comment of this video. For instance, in statistics, I see a lot of people, coming up with all this statistical analysis and averages and means and standard deviations and all that. And if they just used common sense, they would end up with a solution that is much more practical and viable. But anyway, let's finish this up. So the answer is 99. We did finish. There are many ways to rethink this. There are many, many ways. After the fact, after I realized this is actually 3, we can think of this as 1, 1, 1. If you split the 2 into 1 plus 1, and you put 1, 1 here and 1, 1 there, really, we have the sequence 1, 1, 1. But that is dangerous because the last term is 0 in this sequence. So the 1 wouldn't belong there anymore. Yeah, only for full sets, you can think of that as 1, 1, 1. Anyway, the answer is 99. There are a couple sums that are very, very important, useful, and that is the sum of the first n numbers. So example 10, very, very important sum. So if we add n from n equals 1, let's start with something simple, 5. That is, no, so n just means plug in the number and don't do anything to it. So 1, 2, 3, 4, stop at 5, and then we're done. So we can simply just add this in our heads. 3, 6, 10, 15. The answer is 15. No problem with this. So that's what we mean by n, or the index. It just means the number in sequence. Example 11. What if we have the sum from n equals 81 to 88 of n? Well, that's not a problem. It is 81 plus 82 plus 83 plus 84 plus 85 plus 86 plus 87 plus 88. That's where we stop. So we have to figure this out. I'm going to do some computations on the side. We have 1, 2, 3, 4, 5, 6, 7, 8. And we can think of this as 8 80s. You know, we can break this up into 80 plus 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 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8. So 80 times 1, 2, 3, 4, 5, 6, 7, 8 is, so 80 times 8, I know that is 640. And then 1 plus 2 plus 3 plus 4 plus 5, we already know is 15. So now we just need to add 6, 7, and 8. So plus 6 is 21, plus 7 is 28, 36. So we just need to add 36, and then we get 676. So the answer is 676. Okay. Example 12. What if we have to add from n equals 1 to 20n? Okay. So this means add 1 plus 2 plus 3 plus all the way up to 20. You know, 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 plus 11 plus 12 plus 13 plus 14. I don't know. I think I lost count at one point. But anyway, we have to count them all to 20. And you may be thinking, yeah, how? I mean, we can use a calculator. But let's start being a little sneaky about this. Okay. I'm going to write down a few of the terms, 2, 3, the first few terms, and then a few of the last terms, such as 18, 19, and 20. This is one way of figuring this out. By the way, I didn't think of this on my own. Somebody showed me, and then I'm just repeating it. So 1 through 20. And then let's write the sum in reverse order underneath. 20, same sum. So 20, 19, 18, all the way down to 3, 2, 1. So we have this sum 1 plus 2 plus 3 all the way through 20, 1 plus 2 plus 3 all the way through 20 twice. Now let's add them. So we have twice what the answer should be. But we can add them differently. 1 plus 20 is 21. 2 plus 19 is 21. 3 plus 18 is 21. All of those sums are 21 because on the top, as we go up by 1, on the bottom, we go down by 1. So we cancel off the going up and going down, and we always end up with 21. 18 plus 3, 21. 19 plus 2, 21. 20 plus 1 is 21. So this is really a bunch of 21s. How many? Well, this is counting it. 1, 2, 3, all the way up to 20. So we have 20 times 21s. 20 of them. So 1 plus 2 plus 3 all the way up to 20 is equal to 21 times 20. But wait a minute, that's 2 of those. So we have to divide by 2. Yep, and that is 420 divided by 2. So the final answer is 210. If you add 1 plus 2 plus 3 all the way up to 20, the final answer is 210. Well, why don't we count all the numbers and see that sigma looks funny? That's why I wanted to show you how a real sigma looks like. There it is. So sometimes when I write it down, it's not as nice looking. Sorry about that, but please realize that is the sigma. Okay, the way it is supposed to look like. From n equals 1 to 100. Well, we can follow the logic we did earlier. You know, if we put the numbers 1 through 100 and then backwards underneath, and we add them the same way as we added the 1 through 20, we're going to end up with each one of those being 101. So this is equal to 101 times how many of those are going to be? 100. But then that is twice the sum. So we really have to divide by 2. And that is going to be, I'm going to write it underneath, 10,100 divided by 2. So 5,050. If you add 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, all the way up to 100, you're going to end up with exactly 5,050. No more, no less. 14. Some sums are kind of funny, such as 1 over n from n equals, say, 2 to 5. Okay, they're not as nice. These sums are very nice, but this one is not as nice. Yeah, so this is 1/2 starts with 2, remember, and ends with 5, and we increase the n, plus 1 over 3 plus 1 over 4 plus 1 over 5. And now we want to put this together. Fractions, however, require a common denominator whenever we're adding or subtracting the fractions. So that means we have to have a common denominator. 60, I believe, is going to work because we need a 4. We need a number where 4 goes evenly into it, and so does 5, and so does 3. And multiply them all together is going to be too large. We need the least common denominator, which is going to be just the number 60. So this is going to be something over 60 plus something over 60 plus something over 60 plus something over 60. And we can change the 1/2 into 30 over 60. This is going to be 20 over 60, 15 over 60, and 12 over 60. So that is 1/5, 1/4, 1/3, 1/2. Yep. So this requires much more work. 30 plus, we have the same denominator, so we can just put them together. 30 plus 20 is 50, plus 15, 65, 77. Let me double check, 50, 65, 77. Yep, so there's the answer. And that answer does not simplify. Sometimes it does, sometimes it doesn't. Example 15. I'm going to use a new piece of paper because this may take longer to explain. -1 to the n over n from n equals 2 to 5. See, the formula can have anything in it. So if we have -1 to the n, remember from our video about sequences, That means that we're going to alternate the signs. Now, we can just put the numbers. Start with 2, so negative 1 squared over 2, plus, it's always plus, negative 1 to the third over 3. So we start with 2, and we work our way up to 5, plus negative 1 to the 4 over 4, plus negative 1 to the 5 over 5. So initially, it looks like we have, well, let's figure this out. Negative 1 squared is positive 1 because that is 2 negatives. Here we have 3 negatives. So we put down minus a third. 4 negatives plus 1/4. 5 negatives minus 1/5. So we end up with the same numbers, except that some of them are going to be added while other ones are going to be subtracted. I'm going to piggyback on the previous example where we already converted into common denominators. So this is really 30 over 60 minus 20 over 60 plus 15 over 60 minus 12 over 60. So I'm using the same numbers and putting negatives where appropriate. And then we figure this out. 30 minus 20, 10, plus 15, 25, minus 12, 13. So the final answer is 13 over 60, and that's it. 16. If we have a sum that starts with, say, 5 and ends with 5, say 2n, that just means that when it starts, it ends. And that means that we just do one term. You know, when n equals 5, we have 10, and there's nothing to add to it because that's where it starts and that's where it ends. So the answer is just 10. Okay, so if the sum starts and ends on the same number, it is just one term. Just one term. And the sum is that one term, and that's it. There's nothing else to do. So now that begs the question, what happens if we start at 5 and we end at 4? And that's technically undefined. That is nonsense, undefined. Doesn't exist, does not exist, whatever you want to call it. This is poorly written or incorrectly written. We cannot start at a number and end. No. That we're not going to make sense of that. We're just going to have regular additions, and that's it. Other sums that are widely known are these ones. Oh yeah. To the n, say start with 1 and let's end with 5. Okay, so the exponent of the 2, sometimes I like to put parentheses, and a lot of people don't, but that means 2 to the n. So that means 2 to the 1 plus 2 squared plus 2 cubed plus 2 to the 4 plus 2 to the 5. Start with 1 and with 5, and move up with consecutive integers. So that is going to be 2 plus 4 plus 8 plus 16 plus 32, and we just add those numbers. I'm going to guess that is 62. let's see, 6, well, those two are 10. Those two are 20. So that's already, yeah, 62. So that is our final answer for that. And, you know, there's all kinds of additions or sums we can have. We can have 1 over 2 to the n from n equals 1 to 5. Okay, mind, that's the reciprocals of those. So we have 1 over 2 to the 1 plus 1 over 2 squared plus 1 over 2 to the third plus 1 over 2 to the 4 plus 1 over 2 to the 5. Okay, so that is half plus a fourth plus an eighth plus 1/16 plus 1 over 32. And then the only way we can add fractions or subtract fractions is if we have a common denominator. So 32 is the least common denominator. Don't multiply all of that out because that's going to get too massive, too big, too huge. So 32 will do. So that's going to be 16 over 32. That's the 1/2. Plus 8 over 32 plus 4 over 32 plus 2 over 32 plus 1 over 32. And sure enough, the answer will be 16 and 8, 24, and 4 is 28, and 2, 30, 31. 31 over 32. There we have it. That is our sum of 1 over 2 to the n from n equals 1 to 5. I want to end with a challenge. And the challenge is this. So example 20. Add the numbers n, so simple. Start with 76 and end with 1. That's going to be, well, with 100. Yeah, there's the challenge. Yeah, let's just leave it like that. So that is 76 plus 77 plus 78 plus all the way up to 100. Try not to count one by one, 76 plus 77. Get an answer and then add 78 and get an answer and add, try not to do that. Try to do it without a calculator. You might have to do some additions and without a calculator, what I mean by that is try not to add one by one by hand either. No, try to find some kind of a clever way to figure this out. Yeah. Yeah, from 76 to 100. And actually, let's do one more, 21. How about the sum from 51 to 100? Yeah, of n. That way, it will discourage you from doing one by one. I was hesitating when I started this one because it's not too hard to figure out adding 20 whatever elements one by one, but this is becoming more difficult to do one by one. And the other problem is that if you do it one by one, then there's a chance we will make a mistake. The reason why I'm hesitating is because I forgot to mention one more topic. Yeah. No, we're going to leave that topic for another video. We're gonna stop here. Sorry about my indecision. Yep. So there. So these are the two challenges for you to do. What is the sum from 76 to 100, from 51 to 100 of just the numbers n? And with this, we will stop our video today.